Welcome to the next lecture, flow classification. When you see a river flowing, sometimes the river flows very silent. Sometimes it is turbulent. When there is a water increase or when it is a running water, it is very turbulent. And if you have a slow moving water or a static water, when you drop a stone, you see wrinkles moving back and forth and coming. When you have a turbulent water going, so when you throw a stone, you will not be able to see the wrinkles. So friends, this is nature. Now, how do we use this natural phenomena for our engineering applications is important. So better we start understanding how can we classify flows, and then from that understanding, we try to use engineering applications for out of it. So for example, if you have a thin water layer and then on top of it you drop oil. So you can see the oil will be on the top and the water will be on the bottom, right? Or it can be, depending upon the density of oil, it can go in the bottom and the water can be in the top. Now this is very clear. We say there is a layer of immiscibility. Now you want to mix oil and water. How do you do it? So the first thing what comes to our mind, we beat the water or the oil and such that we create enough of turbulence. And then you see slowly there is a mixing phenomena happening. So now in engineering application, what do? We try to use a fan which is called as a shear, a fan with a high shear rate fan. It rotates, it shears the water or the oil, and then it slowly starts mixing oil and water. So this idea is extrapolated from the beating whatever you do. So when you beat, you try to disturb the flow. So that's why this topic is very important. So in this topic, we will try to see what is laminar flow, then what are the key characteristics of laminar flow, then types of laminar flow. The other one is turbulent flow, key characteristics of turbulent flow, then laminar flow versus turbulent flow, what is the difference, then what is vortex, why is it very important talked, what is vortex, what is vorticity equation, then how do I characterize the flow, it is by Reynolds number, so Reynolds transport theorem, then introduction of Reynolds transport theorem, then mathematical expression for Reynolds number, and finally few applications. Laminar flow. Laminar flow is a fundamental characteristics of fluid flow distinguished by its smooth and steady behavior without significant fluctuations. So it enters and exits very smoothly. This contrasts sharply with turbulent flow, which is fluctuating and agitated. I said when a river is flowing and there is a rough river flow, then you see agitation there in the flow. So the laminar flow typically occurs at low Reynolds number. We will see what is Reynolds number by the end of this lecture. So Reynolds number is an evaluation parameter for the flow, right? If in this flow regime, viscous flow forces are significant. Okay? So this is laminar flow. So here smooth steady behavior without significant fluctuation. The characteristics of laminar flow is smooth and steady. The laminar flow is fundamentally characterized by its smooth and steady behavior without significant fluctuation. This orderly motion means the fluid particles follow paths that are predictable and do not cross over each other. So one particle will always move in this direction. It stands in sharp contrast to turbulent flow, which is fluctuating and agitated. Small natural disturbance tend to damp out quickly in laminar flow. The key characteristics of laminar flow is Reynolds number regime. The laminar flow typically occurs at low Reynolds number. The Reynolds number is represented as Re, is the primary dimensionless parameter determining whether a flow is laminar or turbulent. The specific range of laminar flow includes 0 to 1, highly viscous laminar creeping motion, where inertia effects are negligible. When it is 1 to 100, the laminar flow with a strong dependency on the Reynolds number. When it is between 100 to 10,000, the laminar flow where boundary layer theory is often useful. So, when there is a flow laminar, so you can see here there is an orange fluid which is ejected, which moves from here to here without any disturbance, which is passing through a blue fluid. When it is passing through, maybe it can try to extract heat, or maybe it can try to do diffusion, possible, right? So, you can now dictate the flow and try to see what is the flow characteristics it follows, such that you can make use of it for some engineering applications. The Reynolds number regime, the laminar flow, Reynolds number is less than 2100. So, the dominance of viscous force in the laminar flow regime, viscous forces are significant and often dominate over the inertial force. That is the difference. For Newtonian fluid such as water, oil, air, there is a linear relationship between the applied shear stress and resulting shear strain. So, in laminar flow, viscous force is significant than inertial force. So, you can see here layers are formed. So, this is VB, this is VT. So, the key characteristics of laminar flow. So, no slip condition. A crucial boundary condition for all viscous fluid flow, including laminar flow, is a non-slip condition. We have already seen what is a non-slip condition. This means to say that the fluid is in contact with the solid surface, assuming the velocity of that surface. For a fixed wall, the fluid velocity at the wall is 0 relative to the wall. So, this means that the fluid flow in contact with the solid surface assumes the velocity of that surface. So, there is a fluid which is flowing on top. This is the solid. So, this means that the fluid in contact with the solid surface assumes the velocity of that surface. For a fixed, this is a fixed wall, the fluid velocity at the wall is 0. The effect of surface roughness, moment there is an undulation on the surface, the roughness comes into existence. A key characteristic is that rough surfaces do not affect laminar flow. This is because the roughness element are typically smaller than the viscous sublayer which is getting formed. So, you know, in laminar flow, the viscous force is dominating. So, the viscous flow forms a thin film. So, what happens is this is the undulation and then there is a thin film getting formed. So, this thin film takes care of all the undulations, that is what we say. The roughness elements are typically smaller than the viscous sublayer. So, in laminar flow, there are two types, one is internal, the other one is external. So, internal, when the fluid is flowing through the pipe, laminar flow. When the fluid is flowing over the pipe, it is external laminar flow. So, the external laminar flow, if you see the velocity profile along the valve, and when you move from the, suppose you have taken two plates, when you have taken two plates, right. So, here what is happening at the wall is 0. So, when you move from the wall towards the other wall or the plate, so this is the y direction. So, if you see the velocity the gradient or the velocity profile is like this. So, VE is the exit. This is for the external flow. When you have an internal flow at the wall, it is 0 and it tries to slowly increase to a level after which it saturates. The slope almost becomes 0. It goes to the center and then it is a mirror image here. So, at the center the velocity will be maximum. At the plate or at the walls, it will be velocity is equal to 0. So, here what happens, velocity will be 0, this is external, and it keeps increasing as the y increases. So, you can see here del is a limit whatever is set. So, you can see a wall here, this is for internal and this is for external. You can see here u is the velocity which moves, r is the radius of the pipe which is given. So, the velocity profile u is given in this manner. The internal laminar flow. The internal flow are those fluid movement that are entirely constrained by a solid boundaries, where the viscous effects eventually spread throughout the entire flow. For example, you can see here irrotational flow regime. You can see here velocity boundary layer, then development velocity profile, then fully developed velocity profile. So, from here you start moving, this is step 1, 2, 3, 4. You see here fully developed velocity profile. So, this is the final. So, fully developed regime is this. So, from here till the time full time is developed, it is called as hydrodynamic entrance region. So, in the previous lecture we saw hydrostatic, here we are trying to see hydrodynamic entrance regime. So, this is where the profile is drawn. So, you can see here. So, this has the irrotational flow regime is this. So, in this region. So, in a pipe you see something like this, right. So, this front portion is called as irrotational flow regime, and then what is outside is the velocity boundary layer, which is outside is velocity boundary layer, and then it is development velocity profile forms. The fully developed pipe flow, this is a classical and a common example of internal laminar flow typically found in long circular pipes. If this is disturbed, what happens is they create bubbles. These bubbles burst and create cavitation erosion along the pipe. In order to avoid all these defects, because once you lay a pipe, it runs for several thousand hours. So, you maintain a laminar flow, these problems will be avoided. When we have it as an external laminar flow, it refers to a fluid movement that occurs past bodies in unbounded fluid stream. So, this is the pipe. So, here you will have the fluid is flowing on top. So, it is unbounded. In internal, it is bounded, that occurs past bodies in unbounded fluid stream. In these types of flow, the viscous effects are concentrated in a relatively thin layer near the surface of the body. The relatively thin layer near the surface of the body. An example of external laminar flow is air moving smoothly over the surface of an aircraft wing, especially near the leading edge, where the flow forms a thin ordered laminar boundary layer adhering adjacent to the wing. So, it is this way before any turbulent begins. So, this is what it is. You can see here external laminar flow. turbulent flow. Turbulent flow is a distinct and a complex flow regime in fluid mechanics. You can see here how the flow, if you put a particle, how does it go, disturb and go. Characterized by chaotic and irregular fluid motion, which sets it apart from laminar flow. So, the key characteristics are chaotic and irregular motion. The most defining characteristics is the disorderly fluid motion involving irregular fluid movement and eddies. This distinguishes it from the smooth and orderly path of laminar flow. So, the characteristics are: the Reynolds number is a primary dimensionless parameter used to determine if a fluid is turbulent. For a flow in round pipe, the turbulent flow typically occurs when the Reynolds number is greater than 4000. There is a transition region between 2000 and 4000 where the flow changes from laminar to turbulent. There is a transition. So, it is important to note that turbulence can sometimes occur at low Reynolds number if flow instability or disturbances are present. The low Reynolds number you can also have. So, I said from 0 to 2000, greater than 4000, it is turbulent. So, now 2000 to 4000 we say it is transition. Anything less, it is laminar. In this laminar also, if the flow instability or disturbance are present, then at low Reynolds number also you can have turbulent flow. So, this is the formula for calculating the Reynolds number, which is a dimensionless parameter, rho v d divided by mu. So, the key, as I said in the past, now what you do is, if you are trying to push a fluid and if you are trying to create bubbles and then push, right. So, that will try to create something like a vortex, spiral action, and this will try to diffuse now material between the two liquids. So, increased friction fraction and role of roughness. If the in the turbulent flow, the friction factor F and the relative roughness R are very important, because here there is no viscous thin film formed on top of the wall. So, here that plays a very, very important role. So, you can see here, this is the D of the pipe, this is the rho of the fluid, density of the fluid, this is mu is the viscosity. So, enhanced shear stress. A significant consequences of a chaotic motion is that the shear stress in turbulent flow is generally much larger than the laminar flow under comparable conditions. So, the shear stress will be large. Okay. This increases shear stress is primarily due to the formation of turbulent eddies, which creates much greater effect internal friction than molecular viscosity alone. So, when we try to compare laminar flow with turbulent flow, the velocity profile, smooth and parabolic velocity distribution flow are laminar, and here the velocity profile is irregular across the cross section. The energy losses in laminar flow is low, in turbulent it is very high. The mixing of fluid, minimal mixing between two layers happens in laminar. Turbulent, you will have intense mixing. The flow stability is very high here, the flow stability is very low here. So, this is a typical laminar flow and this is a turbulent flow. Vortex. Vortex is a region in a fluid that can be a liquid or a gas where the flow revolves around an axis which can be straight or curved. That is called as a vortex. People smoke and release a vortex ring, right. So, where the flow revolves around a axis. So, tornadoes, whirlpools, smoke rings, all these things are vortex. What are the key characteristics of a vortex? Rotation motion. The fluid in a vortex, so this is torus, the fluid in a vortex rotates around a central axis. So, the particle can go around like this, around the central axis, which can be straight or curved. It creates a classic spinning or swelling motion associated with vortices. So, people sometimes smoke and then they release the smoke. When they release it with a proper pressure and instant open. They will see spirals getting formed while smoking. So, that is vortex. So, about an axis it rotates. Vorticity. The vortex is characterized by concentrated vorticity, a measure of local rotation of a fluid particle. Vorticity is mathematically defined as the curve of the velocity field is vorticity. So, vorticity is mathematically defined as a curl of the velocity field. The pressure distribution and core region are important characteristics of vortex. The pressure in the center of the vortex is low than the outside. So here the pressure, just for discussion sake, will be 0 and here it will be P max relative, right. The pressure in the center of a vortex relatively is lower than the outside due to centrifugal force and described by Bernoulli's principle. This pressure difference is what forces the fluid to flow a curved path around the axis. So, why is this going around the axis? Because of the pressure difference. The core region, at the core region of the vortex, the fluid velocity decreases with radius and may reach 0 while the vorticity is typically highest. So, it can come to 0, center point it can go to 0, vortex. So, there are two types of vortex. One is called as free vortex, the other one is called as forced vortex. Free vortex form when the fluid particles rotate around an axis, this is an axis, due to conservation of angular momentum without any external torque applied. So, it is they use the angular momentum, conservation of angular momentum without any torque applied to it is there. So, the velocity, the fluid velocity is inversely proportional to the distance from the center. So, from the center is so V is inversely proportional to R. The vorticity is 0 wherever expected possible at the center core. The water draining from a sink, the whirlpools and tornadoes are created by this vortex only, which is a free vortex. The velocity is inversely proportional to the radius. Smaller the radius, velocity will be higher. So, forced vortex occurs when a fluid is made to rotate. So, you create a spiral or you try to rotate the object, so it creates a vortex. Occurs when the fluid is made to rotate by an external force like physically spinning a container, so that the fluid rotates as a solid body. So, here V is directly proportional to R. So, if it is inversely proportional, it is free vortex. If you are intentionally doing it, is V is directly proportional to R. The vorticity is uniform and the non-zero across the entire fluid in the body. So, the water in a stirring cup, liquid in a spinning washing machine or rotating tank will have forced vortex. So, there are two, free vortex and forced vortex. What happens in the atmosphere in natural is free vortex. So, the velocity will keep increasing when you go outside. So, when V is very high, R will be very low. So, the vorticity is the fundamental concept of fluid mechanics that describes the local rotation motion of a fluid element. So, when there is a element, then how does it rotate a motion of a fluid element? It is a vector quantity, it is a direction quantity that is mathematically defined as the curl of local velocity. Curl of the local velocity vector v is defined by omega is equal to gradient into v. So, this is rotating about an axis, and this is the local rotation motion of a fluid flow. Vortex and vorticity, what is the difference? It describes a swiveling motion in a region of fluid is vortex. It describes how much fluid rotates at a specific point. How much fluid rotates is vorticity. Physical structure can be seen, vortex. Mathematical quantity only it is done. Contains vorticity within it, can exist without forming a visible vortex. So, all tornado, whirlpool, water stirring in a cup is all vortex. Spin felt by a small pedal placed in the fluid flow is vorticity. So, this shows very clearly the difference between vortex and vorticity. So, the vorticity equation can be written it this way: d omega by dt is equal to omega into gradient times u plus v gradient square omega. So, where omega is vorticity, u is the velocity field, v is the kinematic viscosity, and d by dt is the material derivative. So, through this equation you can find out vorticity equation. So, for a two-dimensional incompressible flow, the equation is given as this: v into gradient square omega, where omega is a scalar vorticity perpendicular to the flow plane. Vorticity is not equal to 0, and here vorticity equal to 0, you can see how the things move. So, it can be away or it can be this way. It is along the plane, it is perpendicular to the plane. So, the Reynolds transport theorem. The Reynolds transport theorem is a cornerstone concept in fluid mechanics and engineering, providing a systematic way to relate change in any extensive property such as mass, momentum or energy of a system to change within a control volume. So, Reynolds transportation theory talks about rate of change in any extensive property such as mass, momentum, energy of a system to a change within a controlled volume was talked about in Reynolds transport theorem. Why is it important? Because it provides the essential link between the analysis of a system and a control volume. These two has to be linked, right, which is preferred method in engineering and fluid dynamics. That's why it matters, right. The Reynolds transport theorem. The transform conservation law RTT converts the fundamental law like mass, momentum, energy originally formulated for fixed masses to a form easily applied to control volume, which are much easier to observe and analyze in real time world. So, this is very important. It converts the fundamental laws like energy, mass, momentum originally formulated for a fixed mass to form easily applied to a controlled volume. So, this to a controlled volume, so that you can try to control volume is what you can try to see, measure what is going on. So, the foundation of engineering analysis, most engineering systems involving fluid enters and leaves a region, making a control volume approach more predominant. Bridging to perspective, it bridges the gap between system, Lagrangian and Euclidean approach, allowing the use of whichever is more convenient for the problem at hand. So, we can try to have this. So, why is this Reynolds transport theorem very important? Because this equation says the rate of change of property of a moving system is equal to the rate of change inside a fixed region, control volume. Then it also tries to say the net rate of flow of that property across the surface of that region. So, this is given by RTT. So, RTT is very important because it tries to bridge the gap between Lagrangian and Euclidean approaches. So, for many practical problems, especially with uniform flow at inlet and outlet, this equation may be simplified to rate. This is very important, friends. Please make a note. Rate of the property change of a system is equal to rate of property change inside CV plus outflow minus inflow. The rate of property change for a system is equal to rate of property change inside CV plus outflow minus inflow gives about the Reynolds transport theorem. So, if you represent it in this schematic, you can see inflow during delta t, outflow during delta t, velocity V1, velocity V2. So, now control volume at a time t and delta t, where CV remains fixed in time. So, next here you will try to see system and control volume at a time t, where there is a shaded region. So, here when system is at t plus delta t, it is at a hatched region. So, this talks about the Reynolds transport theorem. So, the application is the derivation of conservation law, conservation of mass, continuity equation, and continuity of conservation of momentum. See, in all these things you will see mass, momentum, and then energy. Conservation is very important. You can use all the three, use any two or any one. Right? The application derivation of conservation of mass, conservation of momentum, and conservation of energy. So, RTT helps derive the continuity equation, which is used to ensure that what flows in minus what flows out equals the accumulation of mass inside a control volume. What flows in, what flows out, whatever is there, if it has to be 0, the difference. If there is not a 0, then what is getting accumulation of mass inside the control volume. Example, ensuring steady flow in water pipes and in open channel flow. So, you measure in and measure out. This is conservation of mass. Conservation of momentum applied to calculate the force exerted by the fluid on pipe bends, nozzles, turbine, jet engines, where relating to inflow and outflow of momentum changes to net 0. So, this is where momentum comes into action, and conservation of energy used to derive practical forms of energy equation such as Bernoulli's equation or energy balance in the system like pumps and heat exchangers is law of conservation of energy. So, RTT is trying to link rate of property change for system equal to rate of property change inside CV plus inflow minus outflow. This is RTT. So, you see where are the applications they are doing: conservation of mass, conservation of momentum, and conservation of energy. So, the engineering systems and devices where the fluid is flowing through a pipe, duct, or an open channel. So, here the planning and analysis of water supply network, sewer system, air conditioning ducts all rely on RTT. Why RTT is important? Because RTT is going to give, the equation says the rate of change of property for a moving system is equal to rate of change inside the fixed region plus the net rate of flow of the property. So, this is very important, that is why RTT is used. So, it is used in pipes, ducts, open channels, it is used in the pollutant transport, it is used in blood flow analysis also. Modeling changes in blood flow and properties through arteries, organs, and medical devices are done through this RTT. So, friends, what did we see in this chapter is laminar flow. What is laminar flow? What are its characteristics? Then what is turbulent flow? What are its characteristics? Then we saw the difference between laminar flow and turbulent flow. what is vortex, what is vorticity, what are the different types of vortex, free vortex, forced vortex, then the difference between vortex and vorticity. Then we saw RTT, Reynolds transport theorem, the importance of it, and few applications of RTT. So these are the references used, friends, and thank you very much.